Geologic maps and structure. Geologists create geologic maps to show the types, ages, distribution, and orientation of different rocks on the surface sphere. Working from these maps, geologists can interpret the nature of the rocks below the surface as well as above. Geologic maps display the types of rock and ages of rocks through symbols and color. You can view a few of these types of symbols in Appendix A. In Appendix A, you'll see letter symbols for geologic time, map symbols, as well as some common lithologic patterns or rock types depicted by symbols. The forces that act on the rock to change its shape and or volume is referred to as stress. There are three types of stress: a compressional stress or compressive stress, tensional stress or tensile stress, and a shear stress. Compressional stress is a normal stress that tends to push together material on opposite sides of a real or imaginary plane. These acts will shorten the rock. Tensional stress is a normal stress that tends to pull apart the material on opposite sides of the plane on which it acts, resulting in a stretching. If stress is applied to a rock unit, it exceeds its strength, the rock may undergo plastic deformation or fracture. Plastic deformation is a permanent change in the shape of the solid that does not involve failure by rupture. An example of this would be folding, which is a wave-like undulation of formerly flat-lying rocks. Fracture would be when a rock behaves in a brittle fashion and breaks or ruptures. A fault is a break or rupture of the rock where we see movement along one side or the other. Let's look at folding. Here we have a picture depicting a set of rocks folded. This would be like a cross section. We're looking at the rocks below the surface, and these rocks have been folded. We see in the picture that we have some of the rock types being depicted by symbols. Look down below where it says anticline. In this section, there's an arrow pointing up at some rocks that are convexed upward. On the other side, we see syncline. The arrow is pointing to a fold, in this case, that is concave in an upward fashion. We can cut a fold by an axial plane, which is an imaginary line drawn through the long axes of the fold that divides the fold into equal halves. Each half of the limb, or each half, is a limb. So we can see here on the anticline, if we draw that imaginary line through, each side of the line is depicted or showing a different limb. When the fold is considered symmetrical, the limbs are going to be mirror images of one another, and they dip in the same or at the same angle. On the other side, for the syncline, I've drawn in another axial plane. We can see our limbs on either side, and our limbs are pretty much dipping at the same angle. All right, sometimes in folding, when a folded hinge line is inclined to the horizontal, it results in a plunging fold. In map view, a plunging fold would appear as a V shape, as we see here in this image, both top and bottom. If we draw in our axial plane, so here in blue we have an axial plane, we've now split this fold in half. Now there are two ways to identify in this image this is a plunging anticline. We can already see the V shape. This tells us it is a fold that's plunging, but we still need to determine whether or not it's an anticline or a syncline. Looking here, there are two ways to do this. We can use the strike and dip symbols. Over here to the side we have a strike and dip symbol, and this is a straight line with a smaller line coming out perpendicular to it. If the straight line and the small lines are, with the smaller lines pointing out, are pointing away from the axial plane. This indicates an anticline. Another way of identifying an anticline on a map view would be looking at the symbols. Sometimes on the axial plane, you'll see a pair of arrows drawn in. If the arrows are pointing away from the axial plane, it's an anticline. If those arrows are pointing towards the axial plane, they're a syncline. All right, let's look at the different types of faulting. Over here on the left, we have a normal fault. A normal faulting, this is a break in the rock itself. If we were to look at the fault itself, like imagine this as being a slope or a child's slide. The side where the child would be sliding would be the hanging wall or the head wall. The section that would be underneath them was considered the foot wall. If the hanging wall moves down the slide or down the slope in the normal direction, it's creating a normal fault. Over here on the right, if we look again, in this case, just like a child's slide, we look at how the rock has moved on that slide. Well, the rock has moved up the slide. The hanging wall has moved up the slide. This indicates a reversed fault. Another type of faulting is a strike-slip fault. This happens with shear forces, and this is where we just see, like on the San Andreas Fault, where we have two sections just sliding past one another. Now this would be looking from above, so this would be like an aerial photograph. So if you could imagine these two red blocks were originally a road that would have connected together, and now it's offset. Well, when we look at that road, if we pick a side to stand on, it doesn't matter which side you stand on. We stand on one side of the fault, so I'm going to stand over here on this left lateral. I'm going to stand on this white arrow here and look across to the other side. And I look to see how it's moved. Well, looking across on this left lateral, looking across the fault, I see that my road or my section has run to the left. This indicates a left lateral. Even if I were to stand on the other side, so if you can imagine yourself on the other side, turn the other direction, and looking to the other side, I would still see that road moving to my left. Same thing over here on the other side with the right lateral. If I were to stand over here on this white arrow and look across, I see that my section has moved now to my right. So this is a right lateral slip. Now we need to look at some of the symbols that we might see on a map. One symbol we might see is what's called a strike and dip. Strike and dip measurements are used to help define the orientation of the rock units. A strike is a compass direction of the line produced by the intersection of an inclined rock or fault with a horizontal plane at the surface. Dip is the angle of the incline for the rock unit or fault from the horizontal plane. So if we looked at this image here, we see a set of rocks that are actually dipping down at an angle. And then we have this section that's been drawn in here against the rock, this box that's been drawn in here. And this box is showing us where the horizontal plane would be. If we measured from the rock down or up to the horizontal, or from the horizontal down to the rock, we would see on this one about a 30-degree angle. So this rock is dipping at 30 degrees. On here, in this image, is drawn what's called the strike and dip symbol. The strike is that compass direction with the bedding, and the dip is coming in perpendicular to that compass direction and showing us the direction of dip on the beds themselves. So the strike is out to the north, and the dip is at 30 degrees. In your assignment, you're going to be asked to read off the information from a strike and slip from a map. It's going to be something like this one here in your lab manual. We see here, this is a map view. They told us in the map where north would be. So if we were looking down from above, from an airplane or something, we know that north in this map is up here to the top. we have this dike that's running through, and that dike has a strike and dip symbol next to it. It's indicating how this dike is dipping. So we need to put in the strike information and the dip information. So we need to put in that strike or compass direction, and then the dip and the dip's direction. Right? So the first thing we need to do is take a protractor and put it on to the strike and dip. And you notice that the protractor has been set up so that 0 on the protractor is actually going towards north. We also have it set up so that this protractor is set up, it's going 0 to 90 to this degrees, so that we see a piece of that strike and dip falling into the north section. If this had been striking and dipping the opposite direction, I would have flipped the protractor over, still leaving 0 at the north, but then we would see the protractor sitting over here with 90 sitting out on the other side. Alright, now some other things that I need to identify before I start putting in the strike, its compass direction, and the direction of dip and the angle of dip. I need to determine the other directions on this map to start with. Now you can do this by just visually, but I'm going to draw it in. I'm going to put in here some lines, and I'm going to set in here where my north, east, south, and west is. So now I have that information. The next thing I want to do is take that strike from the center there and draw out. Now you can do this by drawing on the paper, but you could also take a straight edge or a piece of paper and lay it onto your protractor and look at where does that line up on your protractor over here. Well, in the case of this one, we can see how it's coming out to about 34 degrees. Alright, so let's come back up here at the top. We want to start filling in the strike. Well, first off, our line is going from the north direction, so it's in the northern quadrant, and it's actually striking out down to the east. It's going north. We already have that in our problem. 34 degrees to the east. So we're going to put that in. North, 34 degrees to the east. Now, those fell off the map just a little bit, but you kind of saw them come in. We're putting a 34 in the east up there. Alright, now let's look at the direction of the dip. When we come over here and we look at the direction of the dip, well, the direction is going out to the northwest. So we're going to put northwest in there. And we read the dip directly off the symbol. The dip is actually given to us. We don't have to measure this one. It's 65 degrees. Alright, in the next section, you're actually going to finish in filling in some information about the rock beneath the surface. You're shown the map view, but you're not told what it looks like below the surface. You're going to use what you see in the top plus the strike and dip to fill in the rest of your map. Well, in this one, I need to come in and I need to take my protractor again, but this time I need to draw in my lines for my beds that are beneath the surface. According to my strike and dip symbol above, all of these beds are dipping down 40 degrees. So I'm going to start by putting this protractor on my contact point between my sandstone and my shale here, and I'm going to draw out at 40 degrees. This allows me to put a line below the surface. I'm then going to take this protractor, I'm going to shift it over to this next point as well and draw another line out 40 degrees, so that I end up with two lines that look like this. Now I need to finish the symbols beneath the surface. If I'm looking here, this whole section on this end, if this is a shale up here, then all of this down below needs to be a shale here. If this section is sandstone, as I turn the corner and come down, this is also a sandstone, and then another shale. So I need to come in and fill in my symbols that are depicting the rocks that are shown at the surface. So I'll draw my shale, draw in my sandstone, draw my little dots, and draw in another shale. Now I've completed the image. Alright, so that concludes the instruction for this lab.